Okay, thank you, Miguel. So I thank you very much also for organizing this meeting so well. Also, you and your organizing committee did a great job. I had to do almost nothing, so didn't even respond in time sometimes, and everything still worked well. Thank you. If you looked at what I promised to teach you, maybe I promised it sometime. It's a one semester lecture actually, and I have to compress it to 1.5 or 3 hours, so it's a bit tough. I'm usually used to write on blackboards. I mean, I'm talking about cavity quantum electrodynamics, which was introduced. I mean, this paper of Jaynes and Cummings was submitted when I was born, so it's about the same age as me. So I'm used to blackboards, but I'll try to write on the screen here. So we will split split this into 2 parts. So the first part will be like the conventional lecture style, with writing and presenting the basics of the Jaynes-Cummings model, which half of you probably know very well, but maybe the other half not so well. And tomorrow we will go more to applications in my recent research. And in between there will be Andreas showing that experimentalists can now do a lot, which theorists, when they introduced it, thought it was just a Gedankenmodell for their discussions. But nowadays, people have realized this in the lab. And the basic thing is, so it boils down to something nowadays where we have a resonator, which yesterday we got a very beautiful introduction into resonators. So you need at least 2 mirrors, which somehow confine some field. And this field will create standing waves in this resonator. And as we have seen yesterday, beautiful modes will appear, which are the eigenmodes of these resonators. Could be a closed volume or not. And somewhere in this resonator, we put an atom with an internal structure of energy levels. And this atom is coupled to the light field. I mean, in an ideal world, we would be finished. But of course, we know that mirrors are not perfect. So there is sometimes some photons escaping through the mirror. And sometimes, if an atom is excited, it will also radiate to the side and not only to the mirror. And we associate some rates with this. The bad thing is we get dissipation. The good thing is we know what's going on. If we would have the perfect Jaynes-Cummings model, it would not be good because it would do a lot of things, but we don't know. So we need to get some information out, but we can also put some information in. And so we can send the laser through the mirrors. And, but we can also send some light directly onto the atoms. And yeah. Oh, I see there's something cut on my, so I have to make a line. Where, how far do we see? Here. Here is my stop line. No? It's even further here? Here? Ah, okay. Yeah, and as I said, it's good to, I can shift this now into visibility. So the whole thing was started when the maser was around, and people tried to do some calculations for a maser on the quantum level. So the whole idea is to make the most simple, non-trivial model of interaction of light and matter. So it was really a toy model, and they didn't think a lot about really building this stuff. They thought that this could describe a maser in one more, in a simple sense. The full theory was known, of course. Yeah, there is relativistic quantum electrodynamics, which was the real theory behind all of this. Lorentz invariant, relativistic. So you have a quantized form of the Dirac equation and the Maxwell equation, and but it's a mathematically complex theory, and you cannot hope to treat a laser within quantum electrodynamics in a reasonable way. But you still be able to study some of the quantum phenomena. So really quantum phenomena of light and quantum phenomena of atoms, this was boiled down to this toy model of Jaynes and Cummings, later on becoming known as cavity quantum electrodynamics. And so the idea was to study, so to say, quantum dynamics of light and matter in the simple sense of atoms. And it took quite a few years, more than 20 years or so, that people really started to trying to implement not the maser, but trying to really implement what's called the micromaser, sort of a toy model of this cavity quantum electrodynamics. And there were first experiments in the 80s in Munich and Paris, and then in other places. I think Harvard was also, and later on with atoms. And the thing was sort of the first implementation. So experiments were in the microwave, and for this to really make a good resonator, because we heard all the blackbody photons are around, you needed really low temperatures, so people used superconducting resonators. And this actually became fashionable in the last 5 to 10 years again. There was a renewal of all this superconducting resonator cavity QED. And for the atoms to have sort of energy levels in the right range, they had to prepare atoms in Rydberg states, which is a bit tricky, of course, but it was possible. Nowadays, you can make your atoms artificially with Josephson junctions and other superconducting stuff. But people also tried the optical way, and in the optical way, what could be done was to build extremely good mirrors. So at some point, people could make Fabry-Perots with almost 1 million finesse. So again, you were able to implement something with this in this regime. So there were optical supercavities, and there was also now the control of alkali atoms, so all the laser cooling, and if you put this together, you have sort of a chance to make such a cavity QED systems. And soon when the systems were, a lot of the Gedanken experiments could be realized. These Gedanken experiments were like simple things like superposition of atomic states, but there was also atom field entanglement, which played a role and could be studied. And later on, it was seen that this could be used to do all kind of quantum information processing. It was also seen that there is interesting physics in the so-called open system dynamics. So if you have a quantum system and couple it to the environment, it's not only bad, it's also introducing interesting physics to be studied. And at the end, it was also a toy model for the simplest implementation of lasers. So in principle, if you have one atom and two mirrors and some way to pump the atom, you have a laser. So that was also one of the motivations, first to think about these models and later to really trying to implement of them. Nowadays, the whole industry of quantum information processing is more or less based on this type of models. Still, we know, of course, that the full theory is the quantum theory of light and matter, so you have to do relativistic QED with all its mathematical challenges, which can be solved, but of course it's not able to boil it down to such very simple systems. So you need a lot of simplifications, and I will just write a few of these simplifications down. To transform sort of QED into something easily treatable. Yeah? First is that the experiments are fixed in a lab and the atoms are sort of slow. So we can relax a bit the full relativistic invariance and choose a fixed reference frame. Which is sort of the laboratory frame. This helps a lot to simplify the things. Then we don't quantize the whole universe, so we choose a finite volume for our quantum theory. And this finite volume has the advantage that now we have sort of a lowest possible the longest possible wavelengths and the lowest possible frequency. So we have a cutoff in the infrared. And also, if we go to very high frequencies, we discard those. Those are not taking part in our dynamics. So we also cut off the high and low frequency part, and by this get rid of a lot of the divergences of QED already. Then we also assume that our atoms are slow in the sense compared to the speed of light. So they still can be very fast in the sense for the experiment, but they're sort of slow compared to the speed of light. So we don't have to use the Dirac equation. We can stay with Schrödinger, which is mathematically much simpler. And then there is another simplification. So what we do is we make our quantum theory of light and we make our Schrödinger theory of the atoms, and then we couple them in perturbation theory. So we don't fully quantize the complete atom field, the coupled atom field system, but we assume sort of we have sort of a quantized radiation field, and we have our atoms, and they are coupled in perturbation theory. So we quantize atoms and fields separately. And the interaction is sort of and this is all very nicely, for instance, presented in many books, like the book of Cohen-Danucci, Photons and Atoms. So it shows in the whole book that there is a systematic way going from sort of the full theory to this smaller theory. So what we at the end now just take, what do we need? We need some quantized light field in a box, And so we quantize it without any charges, sort of in a sort of empty box. And we have our Schrödinger atoms here somewhere. And these things exchange sort of energy via the so-called dipole coupling. So this is actually the standard minimal coupling used in quantum electrodynamics, just in the Coulomb gauge, and using proper gauge transformations, we can transform this sort of unique minimal coupling between matter and light fields into this dipole form. So it's extremely quiet down back here. So is everybody bored, or is nobody following me? So please, in the latter case, you can complain. First case, I don't care. You can do something else. Okay, now let's see, can we do the, what do we do with quantized radiation field in a box? So again, we know we already have chosen a reference frame. Yeah? So we have an inertial system, and hence we can use electric and magnetic fields. So we don't have to use the electromagnetic field tensor to describe our radiation, so we can use E and B. So that's not an approximation, it's a choice of frame. It's only that when we change the frame, it's a little bit more work. Yeah? Than with the relativistic formulation, but it's more intuitive to work with E and B. And if we have no charges, and the Maxwell's equation, yeah, we can express them via this 4 potential. So we have a potential phi of x and a vector potential which depends on x and t. Is there a cutoff on this side? No, there's no cutoff on this side. So we have these 4 fields, and just to remind you, the electric field is just the gradient of phi plus sort of the derivative of the vector potential, and the magnetic field is just the rotation of A. And we, for simplicity, choose the Coulomb gauge. So we assume the divergence of A is 0 and phi is time independent. So in this case, in this way, we put this into Maxwell equations, and we all know the result is the wave equation for the vector potential A. So the wave equation is like 1 over c squared d over dt squared of A. Oh, maybe I leave this at the end. Plus the Laplacian applied on A is 0. And of course, we have to take care of the boundary conditions, which leads to the modes that we are using. So as we have nicely seen yesterday, we can do a mode expansion of this field. So this A, and now we have a finite volume, so it's a discrete sum. So there's only, these modes have numbers, and we saw the 0, 0 mode is sort of the one with the, well, actually 3 numbers, there's longitudinal and transverse numbers, but we put all these numbers into a single number k, and then there is some coefficient times this mode function, and as it's an eigenmode, its only time evolution is a harmonic time evolution. And we want our fields to be real, so we add the complex conjugate, and I might sometimes forget this, but it's always thought to be included. And this has sometimes the name A plus of x and t, although it has the frequency with the minus sign, we still call it the positive frequency part of the field. And as we have seen, the mode functions fulfill Helmholtz equation with the boundary conditions. So the UK of x the Helmholtz equations over there. Somehow Blackboard is still a little bit different. So we have sort of the Laplace plus omega squared over c times UK of x is 0 plus boundaries. Anyway, as theorists, we don't care too much about the shape of these modes. We ask our mathematician friends, and they tell us that these modes for any finite volume will find an orthonormal basis set. These are, if we put this set together, they form an orthonormal basis set. So it's nice to calculate with them. And of course, the electric and magnetic field are also then proportional to these modes. So there is a mode expansion for the electric and magnetic field as well. I don't know if I have to write it. Maybe I have it on my manuscript, so maybe I write it. So if we write the electric field, it's I times sum over k, and then I now know why I write it. You do something which looks funny. You choose a prefactor of the form h bar omega k over 2 epsilon 0 times uk of x. That's really the mode function. And then what is left is a dimensionless constant times this harmonic evolution factor. And then we have to add the complex conjugate. And this way we smuggle h bar into our Maxwell theory. So there is still Maxwell, this is still Maxwell theory, but this is just a clever choice for later. And now suddenly we have h bar in our theory. And we notice that this amplitude, so the amplitude of the mode, because it's a normal mode, has a harmonic time evolution. So it's actually easy to transform it into a quantum theory by just changing a few letters. So we replace these alphas by the corresponding annihilation and creation operators of the underlying oscillators. So the field quantization in this form is very simple. But it can be shown that it's exactly equivalent to the canonical quantization or Quantelung quantization as it's done, as it should be done by writing the proper commutators of E and B in the relativistic case, transformed to the right frame. So we end up exactly with the same, but this way the trick is sort of, it looks a bit simpler. So our alpha k's are just replaced by operators, and they are denoted by A. And sometimes I will write a hat to remind that this is an operator. Sometimes I will then drop the hat because physicists are notoriously lazy in writing unnecessary things. Yeah. Yeah. So we have these operators, and in order to make them harmonic oscillators, we have to sort of fix, is this, yeah, the commutation relations. So we want that all these A's commute for different modes, because our mode functions are orthogonal, so they're independent modes. Except that the A and A dagger of the same mode does not commute. So this is AK dagger is AK prime, sorry, there's a prime. Yeah. So that's not very new, but when we do this, we see that now the electric field transforms into a field operator. Yeah. So with the same choice, the electric field now becomes a field operator, and the same with the magnetic field. And the only difference is that instead of the alphas, we now have these operators standing there. And now we can calculate the whole, the total energy that we have in our volume, because finally we want to have the Hamiltonian, although we could also guess it. But if we calculate the total energy in the volume, sort of it's the integral over the volume, epsilon, okay, volume integral. We have to square plus c squared, no, c b squared of x and t. And if we introduce now our operators here, and work out the integrals and use the orthonormality relation of the mode functions, we end up with the known Hamiltonian, which is then just 1/2 sum over all of these modes, h bar omega k, and there is a k dagger, ak plus ak dagger. So we get a very simple expression, and of course we know that with the commutator we can also convert this into ak dagger plus ak dagger ak plus 1/2. So that's the standard form. So we have now our Hamiltonian for the field in the system. So this is h sum over k, h per omega k, ak dagger plus 1/2. And we change the name. So what we in the harmonic oscillator call an excited state, we now call a photon. So excitation is a photon. Yeah. So the excitations of these oscillators, which are not oscillators in real space, these oscillators are describing the amplitude of a mode. So there is no real space analog on the operators. They are just virtual operators. And this excitation of these operators we now call photons. So the second excited state is a two-photon state, or two-photon state is also the first excited state of two different modes. So yeah, what if we now go to this extreme simplification of Janes and Cummings, saying that we now consider only a single field mode. So the simplest limit is sozusagen only one mode, and so the harmonic oscillator, the Hamiltonian, which we later use for our Janes-Cummings model, is just this one, and we sometimes even forget about the 1/2 because it's just a constant. Of course, a constant has interpretation in terms of vacuum field energy, but that's already not very useful anymore in this simple form of the theory. But what we notice, if we look at the electric field now, so the electric field operator has some prefactors, but at the end it has a mode, it's proportional to the mode function. I have to create a bit of space here. And it's linear in the A and A daggers. So it is something like A plus A dagger, because if we have one mode, actually we don't even need the index K anymore. The same thing is that the magnetic field, it now depends a bit on the choice of the phase of the mode functions and the origin of time, which one is which, but the magnetic field is then proportional to A minus A dagger times I. One could also do it the other way around, it doesn't matter, but what we see is, we know from the normal oscillator that this is something like our X, and this is something like our P. So the electric and magnetic field play roughly the role of a position and momentum, or in a more general form, quadratures of the electromagnetic field. Now we can just claim a few things to look at special states. So now we have the operators. It's interesting what is sort of the wave functions or the states of our field. And this would be at least one lecture of its own. Yeah. But it can be shown that if all of the oscillators are in the ground state, and if we have a single mode, the ground state we call it now vacuum state. So the ground state is the state where there is no excitation or no photon in the field. We usually write it as a cat with a 0, meaning sort of there is no photon in the field, and we give it the name vacuum state. And we see that this vacuum state, of course, has no photons, so the expectation value of the energy is 0 or 1/2, depending whether we take the 1/2. Yeah, it has no photons, and it has no field on average. Yeah. So generally, for any state with n photons, we can show that the field expectation value is 0. So we have sort of the nth state of the system, which is our n photon state. Yeah, we know this n photon state now has the energy of h bar omega times n, and I'm sort of now ignoring more the 1/2 here, because this is a simpler interpretation then. I don't have to write the 1/2 all the time. So the energy of this state has n quanta, but the expectation value of the electric field, so we have to write n, and then we have this sort of a plus a dagger inside here. So actually it's only a proportionality. I leave out for brevity all these things, but we know that the a and the a dagger, they add or remove one excitation, and the eigenstates are orthogonal, so there is no field. So no matter how many photons there are in the cavity, on average there is no magnetic field and no electric field. That's maybe not so surprising, but so because we know that the phase uncertainty, there is a sort of phase energy uncertainty relation for electromagnetic fields, and if we fix the energy, we cannot know the phase, and that's why our field expectation values are all 0, but we can calculate the variance of this one. Where did I calculate that? So we can calculate the variance of the electromagnetic field operator in an n photon state. Yeah. And we see now, after some time, so we have still this h bar omega in front from the square of this factor that we choose, but there is an n, and now we have to calculate the square of this, and we see that now we have terms where there is a and a daggers. So this whole thing is proportional to the photon energy, and then we get sort of 2n plus 1 here. So we get an uncertainty in the electromagnetic field. So there are field fluctuations which grow with the number of photons. So if we have a high photon number eigenstate, it has no average field, but it has enormous fluctuations. But the funny thing is that also for the n equals 0 state, we have fluctuations which are called the vacuum fluctuations. So this is new from Maxwell. Maxwell, if there is no energy, there is no field fluctuations. In a quantum field, we have in principle no energy, because we have left, and this is not a consequence of the 1/2. Yeah? So if we put the 1/2 in here, it does not change anything. Yeah? It's a consequence of these commutation relations. So what we get when we quantize our field is that the vacuum state has uncertainty in the E and B field. Yeah? Yeah, that's true. Yeah, to clarify, so this will even go on later in the lecture every now and then that the field operators down here are constant. So I don't. So in principle, the e to the I omega kt is still in the a's in the second part. Yeah, I just only can state this here. Yeah, there's a little bit of discussion on this in some of the books. I mean, if you look in the recent book by Zoller and Gardner, they discuss this change a bit. But anyway, yeah, yeah, I did not mention it here. Yeah, I agree. Anyway. The thing is, what we sort of wanted to take from this actually is more or less the only the key things is that photon number eigenstates have no average field. So but even the vacuum has field fluctuations. These are two things. So it's obvious that this is not really the way to go to the normal classical Maxwell field. And so for this, and I cannot give a lot of details, one introduces a new type of states, which are the coherent states. So there is, besides these states, there is the so-called coherent states, and they're defined as the eigenstate of this operator A, which we know from definition is not a Hermitian operator, so its eigenvalues are in principle complex numbers. Yeah, they don't even necessarily exist, but they exist. So we can define states of this form. And now we see if we calculate the electromagnetic field expectation value of such a state, it has an average field which fulfills sort of Maxwell's equation in the sense of the Ehrenfest theorem. But we see that these states, they don't have a fixed energy. Coherent states, they have sort of they have an average field, but an uncertainty in energy, or which is as an uncertainty in photon number. So they have photon number fluctuations, uncertainty in energy or photon. Yeah. I mean, in the sense that we consider our photons, which are not free-flying photons, but these sort of quanta in the oscillator. And but luckily one can show that this uncertainty in the photon number grows only with the square root of the number of photons in the coherent state. So if we put enough enough photons into a coherent state, saying if the alpha is big enough, then these fluctuations become small and go to zero. So in that sense, these coherent states are more what we are used to from classical electrodynamics. They have a lot of other interesting properties, but I cannot go further into this now. We go to the next box now. I mean, this is really brutal, I see, because I have not much time. And I start with how do we treat our atom. And again, we can start from classical electrodynamics and start from the classical Lagrangian of a charge in an electromagnetic field. And I cannot really, I mean, this. So everybody should have heard this somewhere during his physics career. So in terms of this potential before, we can write the Lagrangian of this form called minimal coupling form. And if you, there's velocity here, if you derive the corresponding equations of motion for the particle, you get the Maxwell-Lorentz equation for the moving charge. So this is consistent with classical electrodynamics, and without any much talking, we can convert this into a Hamiltonian form and then into a Hamiltonian. So now our Hamiltonian does not depend on velocity anymore, but it depends on the canonical momentum and on position, in principle maybe also on t. And we know that it looks like this. There is sort of this p squared over 2m, oh no, sorry, p minus e a, and I'm sometimes using the c here and sometimes not, but it's again squared plus the electrostatic part. So here we have introduced the canonical momentum, and we did do this because Schrödinger's claim was that the canonical momentum has to be replaced by the gradient operator, whereas sort of the whole expression here is the kinetic momentum, sort of the real physical momentum of the particle. So the kinetic energy is this whole term, yeah. Sometimes also called pi, but not so important. It's more or less for completeness. And Schrödinger, following now, we said we use the recipe, we use Schrödinger atoms. Oops, what happened here? Told us to replace x by a position operator and p by the gradient. The canonical momentum has to be replaced by the momentum. So p goes over in minus EH bar gradient, and x goes over into the sort of multiplication operator. And again, we end up with a Hamiltonian now for our, how much time did I use already? Almost half. Yeah. So we get our Hamiltonian and in principle, what I ignored up here, we still have the Hamiltonian from the field, which we sort of add without too much discussion here. As I said, in principle, one should be a little bit more careful, but for the moment, we just add the field like this. Of course, this is now for a single charge, and even the simplest atom has more than one charge. Yeah. So if we have an atom, we usually have the nucleus and the electron. So we have one proton and we have one electron. So we have two of these position operators, but we can change into the sort of center of mass system and assume that the nucleus is sort of much heavier than the electron, and in this way sort of identify the sort of relative coordinate, the center of mass coordinate with the proton coordinate, and then the relative coordinate is then the distance of the electron to the nucleus. So we introduce the center of mass, which is sort of m proton, x proton, over the total mass, and the difference coordinate is sort of the proton minus the electron. So why do I actually insist on this? The thing is that one has to be a little bit careful then what the x in the Hamiltonian means, because sometimes there is some confusion about this. So now usually we have the Schrödinger equation, and now we have sort of in principle the evolution of the center of mass and the evolution of the relative coordinate, which is sort of identified with the electron, but still we have sort of two types of positions here. But if we are sort of in the sort of infrared or visible range, so even from microwaves, so up to the visible, we know that the wavelengths. So if this is sort of our lambda of the mode, the wavelengths of the mode we are considering, this is much bigger than the size of the atom. Yeah. So somewhere there is sort of an atom, and this atom has a wave function which is centered around the center of mass of the atom, and it has sort of a small dimension d, which is much, much less than lambda. So in that sense, we can then replace sort of the electron position with the center of mass position as well. So we assume that the electric field at the position of the electron is the same as the electric field at the position of the center of mass, and this then gives to the this leads to this called dipole form of the interaction. We can use higher order terms and go on with this, yeah. But we replace sort of the position of the electron with sort of the center of mass position. We only have to be careful when we do derivatives, yeah, because the derivative still has to be done with respect to the relative coordinate. So when we do all this, we end up with the Schrödinger equation for our atom in the field. Which is exactly the one that I wrote up before. And now here we have the gradient with respect to the relative coordinate. Yeah. And we have then the electromagnetic field potential in principle at the position of the electron, but we replace this sort of with our center of mass position approximately squared, and we assume that sort of the derivative of this potential with respect to the electron coordinate is also almost zero. So there is no sort of gradient here in the there is no difference in the field between the nucleus and the electron, and then we still have the Coulomb potential, which contains the relative coordinate and the whole thing times psi of small r and t, sorry. Yeah, so now we can reorder this a little bit. It's a bit of reordering. So we take the Laplacian here and the Coulomb potential together. So the Hamiltonian here has now this standard Laplacian plus the E squared, or actually E bar squared over yeah, 4 pi 0 r. So this is one part. Then there is the part where we have the gradient and the A. And here the trick is that we now assume that this derivative is small, so that we can pull the gradient operator over the second operator. So there is an e to the m, and the 2 is gone, and we can write it in this form times, sorry, the gradient of r, and then there is also a term with e over 2m a squared. Yeah, and here we call this atomic Hamiltonian, and this we call interaction Hamiltonian, and we see that, sorry, there is, I did the mistake again, myself again. So you have to make sure that this contains only, the A contains only the center of mass coordinate in this form of the dipole approximation, and sort of the first part of the Hamiltonian contains only the relative coordinate. In principle, there is also the center of mass momentum. If we are interested in sort of quantum atoms, one can also add the PR squared. Oh, sorry, I need space. I forgot to write it. So there is also the kinetic energy of the center of mass to be added, which was ignored by Jaynes and Cummings, and we will also ignore for most of the time. And so this is sort of the atomic eigensolutions, and then we have a rather complicated looking term here, and there the A squared term is a source of like at least 30 years of controversy, and people are writing about whether it's important or not important, or what it means, or whether we can just leave it away. The thing is that one can go to a naive point of view and say we still have a gauge freedom, so we know we can get the same electric and magnetic field by using any gauge transformation on the vector potential A, yeah, and we can use a gauge transformation which makes the vector potential vanish at the position of the atom. And this gauge transformation, so I cannot, for time reasons, really do everything and explain it, but there is a gauge transformation which can be done with a function minus r dot a of r and t. And if we do this, we know that the A prime, so the regauged A field, gets a gradient of this function, and the potential, we have to add the derivative of this function. And now if we look at the gradient of chi, it's just minus A. So this makes it 0. And here we get something like A dot, R times A dot, which is the electric field. So we have minus R times the electric field at the position of the atom. So now the two terms at the end vanish, but instead we have the term with the new electrostatic potential arises, and we have the Hamiltonian in the form that you find it in most books. So our sort of regauged Hamiltonian is now nothing else at this atomic Hamiltonian we had up there, minus E, I forgot the E somewhere, minus E dot R times the electric field at the center of mass position of the atom, and then there is sort of the free field term. So that's the Hamiltonian in the form we want it. It's the usual sort of dipole Hamiltonian. So here we have the free atom, that's the free field, and that's so-called dipole interaction. If we call E dot R the dipole moment operator of the atom, we have the known mu dot E interaction. There is a bit of debate whether it can be done this way or what to do, but in principle it's more or less an easy way to derive this. So now I used, oh yeah, not too slow, but okay, what's the next step? Let's see. So at some point I will switch to the other presentation style, but I think I can still go on a little bit in a more conventional way. So now we assume somehow we are good mathematicians and we can solve the Schrödinger equation of our atom somehow. So, oh sorry, that's wrong. So the next step is to solve the Schrödinger equation for our atom, and we know that our atom has certain quantum numbers, L and M and N, and somewhere it has a ground state where L equals 0 and N equals 0, and also M is equal 0. Then there is excited state where N is 1, and then there is also the excited state where L is 1 and N is 1, and then we have M equal to 0 plus minus 1, and so on, with more of these states. Yeah. But we assume that our cavity mode has an energy which only fits to the energy between n equals 0 and n equal 1, or any other chosen n. And also we know that our dipole moment sort of is non-zero only if we change the parity, mu. So this operator has parity minus 1. So basically we now, from all of these states, only need a few, and in the most simple case only 2 in our interactions. So in principle our principle sort of the atom has eigenstates with a lot of indices. I mean, there is also spin if we look more carefully, or hyperfine, but let's say it has some eigenvalues. But all of these we again combine in a combined index I, yeah, and we know that if we have found all of these eigenstates, that our Hamiltonian can be written as a sum over all of these eigenstates, 1 to infinity, and then the energy of these eigenstates, if we divide the energy of these eigenstates by h bar, we get a frequency, this frequency omega I, and then we have sort of just the projection operator onto this. So this is the Hamiltonian of all of the bound states of our system, and the same, yeah, and we know that, like for the cavity, that they form an orthonormal basis for the bound states of our electron system. Then we can also see that this dipole moment operator can be expressed in this basis. So this dipole moment operator can be written in the form that we write the unit operator to the left and to the right of this dipole operator, and assume that we only consider the Hilbert space of bound states, where this sum is the unit operator, and in this way we can write this as a sum over ij, and then there is sort of transition operators ij, and then matrix elements from mu ij, where this mu ij is sort of and I hope I didn't mix the order, but otherwise you have to reorder this. And we only take I not equal to j, and these are the dipole matrix elements. And now we are sort of can write down this total Hamiltonian in this eigenstate basis plus sort of the mode basis of the electromagnetic field that we had before. So the whole exercise was to write down this Hamiltonian as a sum over all atomic states, h bar omega I, times sort of the projection operator on the ith states. Then we have the sum over all our field modes, h bar omega k, and we have the ak dagger ak. And then we have sort of this, we expand the electromagnetic field in terms of A and A daggers as well. So we get a sum over k, and also sum over I, j, let's see. Okay, that gets a complicated sum, so it's too much writing. So what we have here is sort of this mu dot E of R of t. Yeah. So our Hamiltonian is now a system of sort of harmonic oscillators coupled to this set of states of the atom. Yeah. And the idea of chains and Cummings was just to use the simplest possible form of this. Yeah. So if you want to do something which is non-trivial, yeah, you need at least 2 atomic states, otherwise not much can happen, and you need at least one of the modes. So what you choose one mode and one atomic state. Yeah. The simplest non-trivial state is one field mode plus 2 atomic states. And if we choose 2 atomic states, we have a 2-state system, and we can identify this 2-state system with a spin 1/2. So it's an effective spin 1/2 system. And with this idea, we finally arrive. So then we can also show that due to the symmetry, the antisymmetry of the mu operator, we can show that the mu I are always 0. So in this sum of over the electromagnetic field modes and the dipole moments, only the non-diagonal elements survive. And if you only have 2 states, sozusagen only mu 1, 2 is non-zero, and the Hamiltonian, it's getting tight. So the Hamiltonian is now h bar omega 1, and then we call this projection operator sigma 1 1 h bar omega 2 sigma 2 2, and then there is plus h bar omega cavity, the a dagger a of the cavity, and then we have some constants which has this factor that we cleverly choose at the beginning, and then we have our mode function which we can choose real if it's a finite volume times this matrix element 1 2, which projects out sort of only the part of the field in the direction of the dipole, and the rest is just the sigma 1 2 plus sigma 2 1. I have to define this, or did I? No, I didn't. And then there is from the electric field, depending on whether we pull the I in front or not, we have an A minus A dagger or an A plus A dagger put here. And this whole stuff out here, we usually abbreviate by 2 g of x, so an effective coupling constant. And to make the definitions complete, the sigma ij are these operators, the transition operators where I is equal to j. Now we can choose we can choose the energy in a way that the energy is, the zero energy is in between the two eigenstates, and with this the first part converts into the well-known sigma z Pauli matrix, and we end up with the Jaynes-Cummings Hamiltonian A dagger A plus h bar omega atom, oops, sorry, well, sigma z over 2 plus h bar g over 2, and there is the a times sigma plus, actually there is 4 terms, a dagger sigma minus, and then there is sort of the a dagger sigma plus the a sigma minus. And then the last thing we have to do is so-called rotating wave approximation, which means that if we look at those terms, the time evolution of those terms, we see that these last, of course, the last 2 terms, they will rotate fast, yeah. Because in the independent case, when the fields are not coupled, they have the same frequency dependence with e to the I. The one is e to the I omega t, and the other one is e to the I omega kt. So the product will be e to the I omega plus omega k times t. So these independent operators, they have a very fast time evolution, whereas the first 2, the difference in these frequencies appears. So they have a slow time evolution. And one can sort of argue or even show mathematically more strict that for the case of an optical transition, we can forget about these 2 terms, as long as the G is in the perturbative regime. So if the G reaches sort of also the optical frequency, this is not a good approximation, but normally this works quite well. And this is now, after a lot of talking, the Hamiltonian that was written down by James Cummings more than, well, in 62, more than 50 years ago. And it's probably one of the Hamiltonians with the most papers in literature written on it. I don't know, it must be enormous, and enormous a number of books. And in the last 10 minutes, I want to discuss the consequences of this, but as it's impossible to do this, I can't write that fast. So I have prepared the emergency slide for this case to finish this now on the blackboard. Is there a laser pointer? So I'm going to a more conventional presentation style. So we have now derived, let's say, under quotes, this Hamiltonian. We could also say we have cleverly guessed this Hamiltonian. And the question is, what are the consequences of this? So now we have a model where the electromagnetic field is described by a quantum oscillator. The atom is described by a spin, which is also a quantum object. And we have this energy exchange term. Usually, the frequencies are of the order of 10 to the 14 hertz, whereas this coupling constant is at least, people try to get it high, but it's usually much, much lower than these frequencies. So leaving out the non-resonant terms is a good choice. And of course, we have to choose the mode correctly. And if we look now at the eigenstates of the unperturbed part, here that we have the zero photon eigenstate. If we put one photon in, we go up this ladder. For the atom, we don't have a ladder, we just have the ground state, which is here of the atom. If we excite the atom, put no photon in, we have also this excited state. And then we can also add photons to the excited state. So we have this type of product basis of this Hilbert space. But we see, of course, that these product states, they are not eigenstates of the interaction part of the Hamiltonian. So if we apply sort of the A dagger sigma minus to this state, it's not reproduced. So this is not an eigenstate, so we have to find, like always, we have to find the eigenstates of this Hamiltonian, and this can be done analytically. That's really the good thing. It would be completely impossible to do something like this in quantum electrodynamics. Even the ground state of hydrogen is a very tough problem without any extra fields. Or hydrogen is not even possible, but something like hydrogen. Yeah. Anyway, we find that now the new eigenstates, which are eigenstates of these Hamiltonians, they come in pairs. So we have the ground state where atom and no photon is in the field. Then we have these first two excited states where there is a mixture of an excitation of the atom and the photon. And we can superimpose this in two orthogonal ways to create the eigenstates of this Hamiltonian. If we are on resonance, they simplify a lot, these eigenstates. So these relative weights, on resonance, the relative weights get 1. Okay, you don't see everything. Anyway, and the eigenstates are just odd and even superposition of sort of the ground state with n photons and the excited state with 1 photon less. And these eigenstates are, in that sense, hybrid objects of field and atomic excitation, and in this way they are called polaritons. This is sort of a sloppy language, but these hybrid states we can call polaritons. And if we do spectroscopy on the coupled system, and this coupling is sort of sufficiently strong, we see that we get these polariton resonances. Even if we start in the ground state, we can excite sort of the plus and the minus superposition of these two possible states, and we get this sometimes called vacuum Rabi splitting. If we look at the dynamics of the system, it also can be very simply solved. We just multiply the eigenstates with the corresponding energy factors. And if we start, for instance, with an excited atom in the cavity, we can express this as the superposition of the plus and minus state in the first excitation manifold, because this is sort of 0e plus 1g and the other one is 0e minus 1g. And if we subtract it, we get sort of the 0e left, and the time evolution then is trivially calculated. We just multiply with the energies, we pull out this common factor, and we see that the amplitude of the ground state and the zero photon state excited state atom and ground state atom 1 photon state periodically oscillate with frequency 2g, or g depending on whether we put the 1/2 in, and we see that the energy coherently transfers between the atom and the field. But that's not really like, it looks like spontaneous emission, so we put the excited atom in and after some time it's de-excited and the photon is in the field, but it's not like normal spontaneous emission because it's completely reversible. We wait another time, the thing is back at the atom. So these oscillations are the famous Rabi oscillations, which you all know and have seen very often. If we sort of stop in between at half time, we see that from the excited atomic state, we have produced an atom field entangled state. So, and this is sort of one of the key processes in all of quantum computing and quantum information. By resonantly coupling sort of a material qubit to another, to a field qubit or some other qubit, we can create entanglement, and this entanglement is sort of a vital ingredient of a lot of the interesting physics happening here. If we have two atoms, we can stop the interaction with one atom and start the interaction with the second atom somehow, and this way entangle even two atoms. And all of this has been done in very beautiful experiments in Paris, and Serge Roche and others partly got the Nobel Prize for setting up such a system and doing all this in an extremely controlled way. The other thing is that there is also a version of this Jaynes-Cunning's model when the two frequencies do not coincide very well, but we have some detuning between the atom and the field. And if this detuning is bigger than the coupling strength, we see that it's like driving an oscillator of resonance. It will more or less adiabatically follow the driving field, and we can express, using the Heisenberg equation, we can express the polarization in the atom in terms of the field inside the cavity or the field operator. I mean, this is really a bad equation from the point of view of a mathematical physicist, because we have operators on two sides which act in different Hilbert spaces, and we put an equal sign here. So it's a bit terrible, but if you know what you're doing, it means that this is restricted to the Hilbert space of correlated states. So only states are allowed where where the expectation value of the dipole moment can be related to this expectation value. So this, if there is other states involved, then of course this equation is complete nonsense. But anyway, we can do this and stack this in again in the Hamiltonian. And now the interaction doesn't look like the conventional Jaynes-Cummings interaction anymore. We now have a dispersive interaction between the photon number and the excitation. And this is mainly the limit where Andreas will be working in after the break. So if you have atoms in the cavity which are not resonantly coupled to the field mode, we get this type of dispersive interaction. And tomorrow I will also mainly concentrate on this type of interaction if we include the center of mass motion. So to make this more interesting, we have to include the center of mass motion. But what we get here is that depending on the photon number, we get a phase shift in the atom, or depending on the atomic state, we get a phase shift in the mode. This interaction is, for instance, used in many of the superconducting qubit apparatus to measure the state of the qubit without sort of creating too much perturbation, because we see there is no energy exchanged anymore between the field and the atom, but still there is a coherent quantum interaction. So surprisingly, I could almost finish what I wanted. So in the, as we've seen above, in a standing wave cavity, this G coupling depends on the mode function, so it is a sine kx. And in the dispersive limit, it gets a sine squared. So we have sort of a term which is sine squared in terms of the center of mass position. So this is like a potential for the atom. So this field mode creates an optical lattice potential in the cavity, and this can be used for very cool physics, as Andreas will show later on. So I used up all your question time, but maybe you can still, well, you can ask questions during the coffee break. I hope the level was not too low for most of you, but yeah, okay, thanks for the moment.